Ismail here from Press to Chemistry. Today we are going to discuss aldol condensation, the reaction of aldehyde and ketone with dilute base or acid to form beta hydroxycarbonyl product. The scope of this reaction is aldehyde and ketones that in the presence of dilute base produce beta hydroxycarbonyl product. It doesn't matter what the starting material are. It can be any aldehyde or ketone to produce beta hydroxycarbonyl product as aldol addition. If you focus on this reaction, this is an ideal reaction to produce carbon-carbon bond. As you can see, carbon-carbon bond here that is generated as a result of this reaction. Similarly, the new carbon-carbon bond produced in this reaction as well. Also, if you focus on number of carbon in this reaction, the starting material contains 2 carbon in first example and 3 carbon in second example, whereas the number of carbon are double in each product. So the surprising outcome of this reaction can be understood through the mechanism of reaction. So first we will try to understand the mechanism of reaction under basic condition. Under this basic condition, any of the carbonyl compound that contains active hydrogen, as you can see in this example, the active hydrogens are at alpha position, which are acidic in nature. So in the presence of base, these acidic protons will remove by the base to produce an enolate which is nucleophilic in nature. This nucleophilic enolate will further react with another unreacted molecule in the medium, as any reaction contains huge number of starting molecule. So the addition reaction will take place between activated nucleophile and unreacted electrophilic molecule to produce addition product with the formation of new carbon-carbon bond. In the end, the abstraction of proton from the medium can lead to produce beta hydroxycarbonyl compound. I want to tell you a trick that how this reaction how you can predict a product of any aldol addition reaction. For example, if you consider a carbonyl compound with general substituent R1 and R2 in the presence of either a base or an acid. Now, pay attention on my writing that you have to draw a V letter V that contains carbonyl at one end, whereas hydroxy at the other end. Now you have to simply place the substituent with the hydroxy carbon. You have to simply place R1 and R2, whereas with the carbonyl there should appear the substituent that does not participate in enolate formation. For example, in this case R2, whereas R1 is the enolate producing end of the carbonyl. I want to simplify this with the real example of acetaldehyde. For example, we have acetaldehyde where CH3 is the R1 and hydrogen is R2. In the presence of base, this will produce a product with V, later having carbonyl at one end while hydroxy on the other end. So the R1 and R2 are methyl and hydrogen, whereas on the other side, methyl iron is enolate producing end, whereas R2 is hydrogen which do not produce an enolate. So move to some more example. The same reaction will take place with acetone, which is a ketone. In the presence of base, you have to draw a V. That V contains carbonyl at one end and hydroxy on the other end, whereas we have 2-methyl as a substituent. One of the methyl produce enolate at one end, while the other methyl will appear as a substituent. So same product is down here. As you can see, there is V hydroxy at one end, carbonyl at the other end, whereas the hydroxy contains 2-methyl. In the middle, we have methylene. This is the methylene, whereas at one end, we have methyl group here. So the mechanism is again similar. First, the base will produce enolate. This enolate, as a nucleophile, react with another molecule of acetone as an electrophile. The addition reaction will take place. The addition product in the end will get proton from the medium to produce beta hydroxycarbonyl compound. Now, some technical point here I want to discuss. As you can see, this example, we have 3-carbon aldehyde, that is propanol. This propanol, in the presence of base, must produce an enolate, but sometimes students get confused that which kind of enolate it will produce. As you can see, there are two alpha carbons, two carbons. One is the alpha, whereas the other carbon is the beta carbon. So either which carbon will produce the enolate. It is clear that the alpha carbon is adjacent to carbonyl carbon, whereas the beta is away from the carbonyl carbon. The carbon attached to carbonyl contains acidic proton which can easily be abstracted by the base to produce enolate. So if you produce enolate at beta carbon, then you can end up with wrong product. As you can see in this example, this beta carbon is producing enolate, which then react with unreacted aldehyde to produce a final product, which is definitely a wrong product. Where in case of alpha enolate, this alpha enolate further react with electrophilic aldehyde molecule, that is the starting material, to produce addition product first, then that abstract the proton to produce final product. So in this example, how you can easily identify the final product? It is very simple. If you draw an arrow here to produce a final product as V carbonyl hydroxy group, a template for drawing any product in aldol addition. Then with hydroxy, draw both the substituent, that is ethyl here and hydrogen, whereas at the other end, CH2 produce, that is R1, CH2 produce enolate, that will now convert as CH, and then there is methyl as a substituent with this group, and at the other side we have hydrogen. So same product is down here. For example of aldol addition, Here you can see the starting molecule is a cyclohexanone which contains alpha hydrogen at both sides which are identical. So in the presence of base, an enolate will produce that as a nucleophile will approach to another starting molecule that act as an electrophile to produce addition product with the formation of new carbo-carbon bond between the two molecules. In this case, the oxygen contains lone pair as a negative charge which abstract proton from the medium to produce a neutral beta hydroxy carbonyl compound characteristic of any aldol addition reaction. The interesting point is when the same reaction occur in the presence of dilute acid, the product is aldol condensation product where alpha beta unsaturated carbonyl produced. The difference, to understand the difference, we need to focus on the mechanism of reaction. As you can see, the starting material is cyclohexanone, which in the presence of an acid will get protonate at oxygen by capturing proton that will produce oxonium ion with positive charge on oxygen. As you know, as a result, the alpha hydrogen becomes further acidic and more activated. As a result, oxygen will pull pi electron toward itself, whereas the sigma electron will produce a pi bond and water molecule from the medium will abstract this acidic proton to produce an enol. Enol is tautomer of cyclohexanone. This enol then act as a nucleophile to react with another activated electrophile of the starting material. So if you focus here that under basic condition we were observing enolate as an activated nucleophile, whereas under acidic condition we have activated electrophile. As you know, by default carbonyl carbon is electrophilic in nature, whereas the addition of proton with positive oxygen further activate this, which can easily react with enol, where enol take part as a nucleophile lone pair from oxygen produce again a carbonyl carbon, whereas pi electron act as a nucleophile to produce a new carbon carbon bond between two molecules. So the same product will produce as under basic condition this one beta hydroxycarbonyl compound is this is the characteristic of any aldol addition, but in the presence of acidic medium the water OH group will further protonate, which will convert the OH into good leaving group, whereas the alpha hydrogen will capture by water in the medium. So the E2 elimination will take place to produce the alpha beta unsaturated carbonyl compound. So this difference can be evident from this example. We have phenylacetaldehyde, because one of the hydrogen of acetaldehyde in this example is replaced by phenyl group, so it is phenylacetaldehyde. In the presence of base, dilute base, the enolate will produce a benzylic position, which will further react with another molecule under basic condition to produce a sustained beta hydroxycarbonyl compound. But under acidic condition, this reaction will produce same beta hydroxycarbonyl compound, but due to the presence of acid, the OH will convert into good leaving group to produce an alpha beta unsaturated carbonyl compound here, alpha beta unsaturated carbonyl compound, which has an extended conjugation with aromatic ring and carbonyl group. To produce the same product from the base catalyzed reaction, the reaction need heating to produce the same product.